Suppose that we want to find the formula for a line that passes through two given points. And so I'm going to give you 2 points, call them x0, y0, and x1, y1. If this were a linear algebra class, which it's not, what we could do is we could say that m times x0 plus b has to be equal to y0. And also m times x1 plus b is equal to y1. This is a system of two equations with two unknown variables, m and b. And it's a linear system of equations. And so you can solve this using the methods of linear algebra. Right? You can say, well, let me make an augmented matrix where these are the entries in my matrix. And then you could do something like complete row reduction so that you make the 2 by 2 matrix on the left look like 1, 0, 0, 1, and then the vector in the rightmost column is going to have entries m and b, right? That's how you solve it the linear algebra way. But there's a way to do this, and it's not that bad. If I had a situation where I wanted to find the formula for a parabola, like this, and it passes through 3 given points, the way I would want to do this in linear algebra would be set up a system of linear equations where every equation would look something like a times x squared plus b times x plus c equals y. And there would be 3 of these equations because I have the points x0, y0, x1, y1, x2, y2. And so when I went to make my augmented matrix, it would look like this. And remember, all of these x's and all of these y's are given to us, so those are constants. The unknown variables we're trying to find after we do the row reduction. After I do row reduction, it should look like this. I can read off my ABC coefficients in the final column. So we're not actually going to do this, right? This is not the right class. I'm just recapping. Maybe if you've taken a linear algebra class before, then this is how it works. And likewise, if I wanted to find a formula for a cubic function that passes through 4 points, then the way I set up my augmented matrix for what I would normally do row reduction on is I would make it have 4 rows for my 4 points and 5 columns. And after I do row reduction, you know that it's going to look like 1's on the diagonal. And then on the final column, it would be like this. Right? So with linear systems like this, we can always find a solution. An interpolating polynomial is one of these polynomials that passes through all points in a given set. Like the last problems I just waved my hands and talked about, you're given some points that belong to a set, and we're finding a polynomial that will pass through all of those points. It interpolates the points when the curve goes through the point. So the minimal interpolating polynomial is just the polynomial that has minimum degree. And the degree of the polynomial, of the degree of the minimal interpolating polynomial, is always going to be 1 less than the number of points that we're arbitrarily specifying. Because if I specify 3 points, then in general I need a quadratic polynomial to go through 3 points. If I specify 4 points, then in general I need a cubic polynomial to interpolate 4 points. If I give you 500 points, then in general I will need a polynomial with degree 499 to interpolate those 500 points. So we're going to use k plus 1 to represent the number of points that should be interpolated from now on in this class. And the minimal interpolating polynomial would then have degree k. And the reason I bring up the linear algebra formulation is because it makes it really easy to understand why the number of unknown coefficients in your polynomial, which is always 1 more than the degree of the polynomial, has to be equal to the number of points in the plane. Because if you don't have enough points, then the columns of your matrix are not going to be linearly independent. And if you have too many points, then the columns of your matrix are not going to be linearly independent. And you remember from linear algebra, that means you can't invert the matrix. So sometimes we use the term degrees of freedom. If k is the degree of my polynomial, then k plus 1 is going to be the number of coefficients that I need to specify in my polynomial. And if n is the number of points I'm trying to interpolate, then my degrees of freedom is going to be k plus 1 minus n. And ideally, we'd like to have no degrees of freedom. If I have more than 0 degrees of freedom, I have a positive number of degrees of freedom, that means I've got more tunable coefficients than I really need. I have more knobs to turn than I actually need to create an interpolating polynomial. So there will be infinitely many solutions. But if my degrees of freedom are negative, then that means my problem is overspecified. I have too weak of a polynomial to fit too many points. And no matter how I turn the knobs, I can't ever make it work. Another little piece of background information is that this minimal interpolating polynomial is unique. Again, because when I showed you the linear algebra, you know an invertible matrix represents a one-to-one function. Matrix multiplication by an invertible matrix is 1-to-1. There's only, for every set of inputs, there's only one output that you get after matrix multiplication. And because I can invert the matrix, every set of outputs has only one unique set of inputs that gets mapped to. So that means an interpolating polynomial with minimal degree has to be a unique thing. We're past the preliminary hand-wavy part of the class now. That part was kind of optional, but hopefully it makes sense if you've taken linear. This is what I need to start with in terms of this is what you need to know for this class. For numerical analysis, we need to know that if I'm given a set of k plus 1 points, and I want to interpolate these points, and my set of points looks like x0, y0, x1, y1, x2, y2, well then k plus 1 is equal to 3 and k is equal to 2. But if I have a set of k plus 1 points, then this is the definition of Lagrange basis polynomials. So that symbol is supposed to be a script lowercase l. The subscript is the letter j. And every Lagrange basis polynomial is a function of x. And it's equal to this. You guys seen this before? This is a product. It's a product of what? It's a product of linear terms. It's a product of linear factors, I guess I should say. It's a product of linear factors where every factor looks like x minus x lowercase I divided by xj minus xi. And the i's include 0 and they include k. And the i's include every whole number between 0 and k. So in other words, there's going to be k plus 1 factors in this product. And as soon as I said that, I knew I said it wrong. There's actually only k factors in this product because we're going to intentionally leave out the factor where I is equal to j. That last little bit in the subscript is saying, I don't want my I index to be equal to my j index because then I would be dividing by 0, right? So we do not want to divide by 0. We leave that one out. And if I leave that one out, then there's only k factors. And these factors are linear in terms of my variable x. All of the xi's are just the x coordinates of the points that were given, and the product is going to go through these. So first I is equal to 0, then I is equal to 1, then I is equal to 2, and then I equal to ... k. The j, the x with the subscript j, is not going to be looped through because the j is telling you which one of the Lagrange basis polynomials you're determining. Which Lagrange basis polynomial are we talking about? So it turns out there's going to end up being k plus 1 Lagrange basis polynomials. In other words, every single point that I'm trying to interpolate through has its own Lagrange basis polynomial. Maybe I should write that out. Every point xj, yj that I'm trying to interpolate has its own Lagrange basis polynomial. So there's k plus 1 of these things. So in exercise 2, it says find the set of Lagrange basis polynomials for the given set of points. And in this, I have 3 points, which means that k plus 1 is equal to 3. And there's going to be 3 Lagrange basis polynomials. I'm not going to write that out. There's going to be 3 Lagrange basis polynomials. One of them is going to be L0 of x. And that's going to be a product where every one of the factors looks like x minus. And I'm not going to include x0 here because I'm not including the factor where I is equal to j, and this time j is 0. So I'm going to skip ahead to x1 divided by x0 minus x1. My next factor in this product is going to be x minus x2 divided by x0 minus x2. And since this Lagrange basis polynomial is a product with k linear factors, and k is 2, well, that's it. I've got a product with 2 factors. Now, x1 is going to be the number 2. So I'm going to write x minus 2 divided by 1 minus 2, and then multiply by x minus 7 divided by 1 minus 7. One minus 2 is negative 1, 1 minus 7 is negative 6. So in other words, I've got like 1 over 6 times x squared minus 9x plus 14. And that's it. That's my first Lagrange basis polynomial. But remember, every single point has its own Lagrange basis polynomial. That was the basis polynomial for the first point. Now let's calculate the Lagrange basis polynomial for the second point. And for the second point, these factors are going to look like x minus x0 divided by x1 minus x0, and x minus x2 divided by x1 minus x2. For the third Lagrange basis polynomial, L2, that's going to be x minus x0 divided by x2 minus x0, and x minus x1 divided by x2 minus x1. Go back and actually fill these in. So x0 is 1. x2 is 7. And this is going to be 2 minus 1 and 2 minus 7. Finally, x minus 1 times x minus 2 divided by 7 minus 1, 7 minus 2. Okay, questions yet? If I had an example that had 4 given points, then I would need 4 Lagrange basis polynomials. And each one of those 4 Lagrange basis polynomials would end up with 3 factors. Does that make sense? Okay, cool. Then the Lagrange interpolating polynomial is defined like this. This time the capital sigma is telling you to add everything up. You guys know that, sorry. I'm used to teaching under lower division classes. You've seen this before. We're going to sum this up from j is equal to 0 to k. In other words, that means there's going to be k plus 1 terms in the sum, and every one of the terms is going to look like the y coordinate of the jth point in my set times the jth Lagrange basis polynomial. So those Lagrange basis polynomials we just found, they show up in the formula for the Lagrange interpolating polynomial. So now, if I want to find the Lagrange interpolating polynomial for the given set of points, this is going to be a sum where I take y0 times L0 of x plus y1 times L1 of x plus y2 times L2 of x. And this is kind of a hassle, because now I have to go back and remember what was L0. They're the same points. So L0 is 1/6 times x squared minus 9x plus 14. Plus 5 times, in blue, we have L1. So it's like x minus 1, x minus 7. I didn't finish fully expanding that one. And then 11 times L2, which is x minus 1, x minus 2. In fact, maybe it's better that way. Sorry for changing my mind about it, but maybe it's better to not expand it, because that might help us see things here in a minute a little bit more clearly if we leave it unexpanded. And so it should be like x minus 2, x minus 7 divided by 1 minus 2, 1 minus 7. Okay. But this is my Lagrange interpolating polynomial. And like the name suggests, this polynomial is a minimal interpolating polynomial. So it has degree 2, and it passes through those 3 points. And because the minimal interpolating polynomial is unique, this quadratic polynomial is exactly the same polynomial you would get from the linear algebra method. Like you learned in linear algebra to make the little augmented matrix, and then you row reduce, and you get the last column gives you your coefficients. I personally know that the linear algebra approach is 4 or 5 times faster than this one. It takes me longer to sit down and think about Lagrange basis polynomials and to multiply them out and add them up and everything. I think it just takes me too long if I wanted like the expanded form of a polynomial. I would just do it the linear algebra way, personally. So you might ask, like, why do we care about this? And the reason is not necessarily just so that we can calculate interpolating polynomials, but you are going to see, it's going to be hopefully abundantly clear in the next 2 or 3 weeks why we care so much about this. But the Lagrange interpolating polynomial is more about establishing a theory of numerical integration and numerical derivatives than it is about just finding what the polynomial would be. Because if you just want to find the polynomial, then do it the linear algebra way. But if you want to develop kind of the whole mathematics theory behind it, that's what we're interested in here in this analysis class. So explain why the Lagrange interpolating polynomial is the minimum interpolating polynomial. This has 2 parts. How do we know that this capital L interpolates all of the given points? This is kind of an interesting explanation, I think. If I were to look at this Lagrange basis polynomial, it has an interesting property. If I plug in x0, this is going to be equal to 1. If I take the same Lagrange basis polynomial and I plug in x1, it's going to be equal to 0. And if I take the same Lagrange basis polynomial and I plug in x2, it's going to give me 0. If I were to take the L1 basis polynomial and plug in x0, it's going to give me 0. If I take the L1 basis polynomial and plug in x1, it's going to give me 1. And if I take the L1 basis polynomial and plug in x2, it's going to give me 0. And likewise, that's supposed to be 1. That's supposed to be a 2. The L2 basis polynomial is only going to give me a 1 if I plug in x2. So let's go back. Verify that this is true. Because this is L1. No, it's 0. 0. This is L1 and this is L2. x0 is 1. x1 is 2. x2 is 7. So I said that for L1, if I plug in x1, no, for L0, if I plug in x0, I should get a 1. And if I plug in x equals 1, then the numerator is exactly the same as the denominator, right? So it should be 1. What if I take the L0 basis polynomial and I plug in x equals 2? So then I have 2 minus 2 in the numerator, which is 0. What if I take the L0 basis polynomial and I plug in x equals 7? Well, then in the numerator I have 7 minus 7, which is 0, which makes it 0. And you can double check that for the other basis polynomials. But the reason we construct the basis polynomials in this particular way is so that the basis polynomial will be equal to 1 when you reach the x value corresponding to that node, and if you reach the other nodes, you get a 0. So then the formulation of this whole Lagrange interpolating polynomial is saying, when I get to the x value corresponding to this node, I'm going to multiply that times the y value. That y value times 1 remains the same. That's what gives you the value of your polynomial, so that guarantees that my polynomial is passing through all the points. So that's kind of the big picture explanation. How do we know that L interpolates all of the points? Really because of this. We are multiplying 1 times the y value for each of the corresponding x values, and all of the other terms in that sum are 0. The second part is, how do we know that L has the minimal degree, which should be k? Well, L should have degree k because we're adding up Lagrange basis polynomials, and the Lagrange basis polynomial is formulated so that we have k linear factors. So when I multiply k linear factors together, each Lagrange basis polynomial is going to have degree k. When I add those up, I still get a polynomial of degree k. All right, any question about that? Okay. I mentioned this before, but that kind of rendered funny when I put it through the PDF, export PDF button. If the matrix formulation is so much easier, why do we care? It's because the whole idea about numerical analysis isn't just about learning numerical methods. It's about analyzing which numerical methods are better than the others. And how do you know if it's better or not, right? You determine how computationally taxing is it through like counting flops. And you also determine how accurate am I going to get? You know, how much error is going to be left in my approximation. And so this is the whole reason we care about the Lagrange interpolating polynomial. And so we're getting pretty close here to the end of my notes, I think. But if you're falling asleep, Kevin, stand up if you need to, stretch your legs. I mean, this is going to be a really, really, really dense proof. And so hang on with me for just a little bit longer. We're going to define the actual error as being my approximation minus the true value. So for an interpolating polynomial, the actual error is going to be a function of my x variable, and it's going to be equal to my Lagrange interpolating polynomial minus the function I'm trying to interpolate. I haven't really mentioned this before, but we've talked about interpolating points. But if I try to interpolate a function, at a set of points, then we're talking about interpolating the function at these points. If I can come up with an interpolating polynomial that passes through these three given points, then I say I've interpolated the function f. Now my interpolating polynomial is an approximation of f over the range from 0 to 2. So that's what I'm talking about. I'm talking about making an approximating polynomial for the function f at certain points. So the actual error can be characterized by this formula that looks a little bit intimidating, maybe. This formula only works when x is between the smallest and largest nodes where you're interpolating. We call the x values where we have the points where we're interpolating the nodes. And so this error formula only works in between the nodes. It does not tell you how the error is happening outside of the nodes. It doesn't apply to extrapolation. And the Greek letter, the Greek lowercase c, also is guaranteed by this theorem to be a real number in between the nodes somewhere that is guaranteed to exist. We don't know exactly what it is. It's kind of like the Cassie that shows up in Taylor's theorem or anywhere else. But we know that it exists. Don't know what it is, but we at least can tell ourselves, yes, this exists, and we can sleep at night. Anyways, the actual error is going to be the k plus 1 derivative of f evaluated at Cassie, somewhere in between the nodes, right? Divided by k plus 1 factorial, so the number of interpolating points, factorial, times the product of these k plus 1 factors that are your x variable minus the location of the k plus 1 nodes. This is the proof. We say at any node where x is equal to xj, right, then one of these factors in the product is going to be xi minus xi. It's going to be 0 for one of the factors. So the error is 0 when you get to one of the nodes. And that has to be true if my polynomial is passing through each one of the nodes or passing through each one of the points. Then that has to be true. Okay, now we're going to assume that x is any other number, so we're not at a node, and it's in the interval between the least and the greatest node, and define a new function. This is my new function that I'm defining just for the sake of this proof. Capital G is going to be the error at a point t minus this product times the error at a given point x, not a node, right, but divided by this product. And again, we have supposed that we are going to fix x, right, when we said let x be a number that's not a node. So g is a function of t. Pretend that the x is a constant. The next claim here says the function g has k plus 2 distinct zeros. They're located at all of the nodes, right? There's k plus 1 nodes, and g is going to be 0 when t is equal to one of the nodes. Because if t is one of the nodes, the error at a node is 0, and also t minus one of the nodes is going to be 0 for one of those factors. So we get all of the k plus 1 zeros that happen because of a node, plus we chose a value x that was not a node, right, for here. What happens if lowercase t is equal to x? Well, then this product is the same as that product, so they cancel, and epsilon of x minus epsilon of x cancels out. So we've got k plus 2 distinct zeros, and that's important. Do you guys remember the mean value theorem from Calculus 1? So the mean value theorem says that, like, if I've got a point here and a point here and a function passing through these points, as long as this function is differentiable, then the average slope, or the average rate of change between these 2 points, is equal to the instantaneous rate of change at one point in between them, right? And so if this was completely flat because those points were completely equal to each other, then there would have to be a derivative of 0 in between those 2 points. And that's what we're trying to rely on here by the mean value theorem. Between two of these zeros, the average rate of change is 0. And so between those, since this is a differentiable function, there has to be a place where g prime has a 0. In between the zeros of g prime has to have a 0, is what we're saying here. And that means g prime has k plus 1 distinct zeros in the same interval. And we can keep doing this. We can use the mean value theorem again to say that if g prime has k plus 1 distinct zeros, then g double prime has k distinct zeros, because g double prime must have a 0 in between all of the zeros of g prime. Okay? So, like, here's the zeros of g. Here are the zeros of g prime that have to fall in between those. Here are the zeros of g double prime, which fall in between those. And each time I do this process, take the derivative, find the zeros, they have to fall in between the zeros of the derivative above it, and that means I lose 1 every time. So I went from having k plus 2 to k plus 1 to just k. And when we keep doing this and we take the k plus 1 derivative, we know that the k plus 1th derivative of capital G still has 1 0 in that interval, at least 1. But it has to have at least 1 0 in that interval. And so we're going to name that 0 Cassie. And I know we don't know where Cassie is. Could be anywhere. But we know it exists, right? So we're going to take the k plus 1th derivative of this g function, right? And that would look like taking the k plus 1th derivative of the Lagrange interpolating polynomial, and the k plus 1th derivative of f, and the k plus 1th derivative of all of this stuff with respect to t. Since L of t is a polynomial with degree k, when I take k plus 1 derivatives, it's just going to be 0. Since this product, the largest degree of t I would get out of this product is t raised to the power k plus 1, and it would have positive 1 as the leading coefficient. We say that's a monic polynomial of degree k plus 1. And whenever I take k plus 1 derivatives of that, the result is going to be a constant. it's going to be k plus 1 factorial, right? Because first you multiply by k plus 1 when you take the first derivative, and then you multiply by k when you take the second derivative, then you multiply by k minus 1 when you take the third derivative, and so on. So you end up with the factorial. So you make these substitutions, the equation that we had before, make this 0, make this k plus 1 factorial, and this is what we get. Then we're going to replace t with c, and c was a 0 of the capital G function after we take the k plus 1th derivative. So what you see here is the right side of this equation, but I replaced the t with c. And then I set the right side equal to 0. And then you rearrange, use your algebra skills. So we add the k plus 1th derivative of f to both sides, divide both sides by k plus 1 factorial, and you multiply both sides by that product, and this is what we get. So like I promised, super dense. It's one of those where if you haven't ever before, you have to reread the proof like 2 or 3 times. You know, one strategy I used to make my way through graduate school is whenever I came across a really dense proof like this, I would read it out loud to myself. Y'all ever do that? You're really trying to understand something, but you don't get it the first time. Like, I swear it helps. Because my tendency when I read something like this is I get frustrated because I don't understand it right away. And when I get frustrated, I start to skim. I start to jump from one sentence to the next without reading every word, and that makes the problem worse and not better. So if you force yourself to read it out loud, then you slow yourself down, you make sure you don't skip any words, and it actually helps with comprehension. So don't give up on it unless you read it out loud to yourself 3 times. And if you read it out loud to yourself 3 times and you still don't understand what's happening, then you can give up. Call it a day. But here are some lessons we should take away from looking at this error formula. At the nodes, the absolute error should be 0. Whenever I'm just close to a node, like when x is pretty close to one of these xi, I'm multiplying by a factor that should be a really small number. And so the error should be relatively small when I'm close to a node. And the converse of that is that the error will be relatively larger whenever I get farther away from any of the nodes, right? If I'm in between nodes. If these nodes happen to be evenly spaced, and this is the hardest one to wrap your head around, what if I've got evenly spaced nodes? I'm trying to make these as even as possible. This point would have a relatively small error when compared to this point. Because this product here is multiplying everything times the distance to each node. And here, since I'm in the middle, I'm going to multiply by this distance, which is pretty big, and I'm going to multiply by this distance, which is pretty big. That's not good for my error. But the really, really bad part is for this point, I'm going to end up multiplying by this distance and this distance. These 2 numbers in orange are a lot bigger than these numbers, right? So for a point in the middle of my interval, the largest factors in this product are going to be about half the width of the interval. But for points that are near the end of the interval, the largest factors that are in this product are going to be almost the whole length of the interval. So you get more errors towards the edges of the interval. That's an important thing to keep in the back of your head. So that's it in terms of new information. Do you have any questions about what we just talked about? Any questions about that proof? Okay, so let's do an example problem. With our remaining, 25 minutes, we should be able to do this. Interpolate the function at the given nodes by finding the set of Lagrange basis polynomials, then finding the Lagrange interpolating polynomial. So this is the set of nodes. This is my function, the nice cosine function. So the points I'm going to interpolate at are 0 and what's cosine of 0? 1. And then pi over 4. What's cosine of pi over 4? Square root 2 over 2. And then pi over 3. And what's cosine of pi over 3? It's 1/2. Okay. Those are the 3 points I'm going to try to interpolate. So whenever I write my first Lagrange basis polynomial, L0 of x, it's going to look like x minus pi over 4 times x minus pi over 3 divided by 0 minus pi over 4 times 0 minus pi over 3. When I go to write my second Lagrange basis polynomial, the L1 polynomial, that's going to be x minus 0 times x minus pi over 3 divided by pi over 4 minus 0 times pi over 4 minus pi over 3. When I write my third Lagrange basis polynomial L2, this is going to be x minus 0 times x minus pi over 4 and pi over 3 minus 0 times pi over 3 minus pi over 4. And since this question is asking me to give the expanded form, that's kind of bad news. That means I've got to work a little bit harder. That means I've got to write something like x squared and pi over 4 plus pi over 3 is like having 7 pi over 12. So minus 7 pi over 12x. And then plus pi squared over 12. Right? Divided by what? Divided by pi over 4 times pi over 3. Divided by pi squared over 12. So we're going to get some weird numbers. like 12 divided by pi squared x squared minus 7 over pi x plus 1. Okay. All right. Moving on to L1, we get x squared minus pi over 3x plus 0 divided by, let's see, pi over 4 minus pi over 3 would be negative pi over 12. Is that right? So this time I've got pi divided by 4 times negative pi over 12. Negative pi squared times divided by 48. Yikes. So negative 48 over pi squared x squared. Whew. And then 2 negatives make a positive. One of the pi's is going to cancel. And it's going to be like, it's 48 over 3. 16 over pi x. Almost done. Getting real close. Let's hope we didn't make any mistakes. All right, then we got pi over 3 times pi over 12, which is pi squared over 36. That's 36 over pi squared, x squared minus 36 over 4 is 9 over pi x. Cool. And so we're almost there. Now we got to put together the Lagrange interpolating polynomial. And the Lagrange interpolating polynomial is going to say, I'm going to multiply the y coordinate times the Lagrange basis polynomial. The first y coordinate is 1, so we would just write out the basis polynomial. The second y coordinate is square root 2 over 2. And then the third y coordinate is 1/2. And I guess it's at this point that my patience runs out and I decide we're just going to switch to decimal. I'm going to keep like 4 sig figs and do this. All right, so for the x squareds, I've got 12 divided by pi squared minus the square root of 2 divided by 2 times 48 divided by pi squared. And then the last term here is giving me plus 36 divided by 2 divided by pi squared. And so that's the coefficient on my x squared, negative 0.39932. Okay, what about x? For x, we've got negative 7 divided by pi plus square root of 2 divided by 2 times 16 divided by pi. Oh, I'm not done, because I still got the third term, plus 1/2. I should really say minus 1/2. Minus 1/2 times 9 divided by pi. So it's, I need more significant figures than that. Give me 5 sig figs here. There we go. Let's do minus 0.059298x. And then for my constant, plus 1. So this is how you check your answer. You say, I can plug that into Desmos, and we do. We say the points I was trying to go for were 0, 1, then pi over 4, square root 2 over 2, and pi over 3, 1/2. Those are the points I'm trying to interpolate. I need to make those bigger. You can hardly see them. You like that. Okay. Obviously, the function I'm trying to interpolate is cosine, so there we go, we've got cosine. But what I'm really interested in is, what about negative 0.39932 x squared minus 0.059298 x plus 1. Aha. So we did it. You know you got the right answer when your interpolating polynomial does pass through the 3 points you tried to interpolate. And notice that, if I ignore the points, it's also kind of a good approximation of the purple curve. It's not exact. Look, I've got some daylight here in between the black curve and the purple curve. But this quadratic that I used, my interpolating quadratic polynomial, is pretty good approximation if I stay inside the nodes. If I stay in between the least and the greatest node, then it's okay. It does a good job.